Gnanam Paramam Dheyam. Knowledge is supreme.
Now we are starting a new investigation, namely remember that this course, the main aim is to study the zeros of a polynomial over a field in one variable, and we want to gather information about these zeros from the knowledge of the Galois group, for example. And when we want to know when these zeros have the formulas. So, in order to understand a zeros of a polynomial without computing, that is the main task, because remember, computing a zero, all zeros of a polynomial is a very big task, and we want to avoid that big one, and just looking at the coefficients we want to extract information. That is the main aim, and to know whether there are formulas or not. So, first of all, there are so many terms vague here, what I have talked. When you say polynomial, where are the zeros, and so on and so on. So, I am going to start a polynomial over many variables, and when I specialize it to the zeros, I will also get my coefficients specialized at the zeros. So, in general, I call, so soon things will become clear when I have a precise notation. So, I consider, so suppose K is a field given, this is given, and an integer, a natural number n is also given, this is given. And I consider a polynomial over this field in n variables. So, I consider this k x1 to xn. This is a polynomial ring in several variables over this. We know the quotient field is precisely the field of rational functions x1 to xn. And we have a group Sn. This is the permutation group on n letters 1 to n. This is a group, and I want the natural action of this group on this polynomial ring first. So, then I want to say that Sn operates on the field, rational function field in n variables over k by what? So, I should tell you when what happens to a rational function. So, take any rational function phi of x1 to xn. Remember, this is a rational function. So, this means it is a polynomial divided by a polynomial. In this, I want to interchange, I want to permute the variables according to the permutation, the given permutation in Sn. So, given any element here and any element in the group sigma, this goes to phi of x sigma 1 x sigma n. So, this is clearly an operation of groups. So, this that means Sn operates on this field by this operation. So, that is very easy to check that this is an operation. Remember, you will have to check two things. If sigma is identity, then you don't, this is also same as phi, and if I have two permutation, then whether I apply individually and then apply the composition, and that is the same operation. So, this is clearly a group operation. Now, whenever you have a group operation, one has to understand the fixed elements, and one has to understand orbits, and one has to understand the stabilizers. This is always, and then we have the information from this. Let me just mention here Lagrange was the one who started this, but Lagrange didn't have this knowledge, language that time of operation or a group or a isotropy. This he didn't have this operation, but he didn't have this language, but he was thinking along the same lines, and his problem was, what was his problem? So I will just mention it before we go into the precise. So Lagrange was looking for what? Lagrange, he was looking for the following. He started with the given f. He started with f, a rational function, phi, rational function in n variables, and he took elements from Sn. Those are the permutations. That time there was not even a knowledge that there are permutations. Later on, when people developed, where people thought about what and what, people developed a language of permutations and more about permutations like transposition, cycles, what are their orders, what are their decompositions, what are their signatures, and so on. And the first systematic study started by Cauchy. This is study of permutation and study of groups also, finite groups especially. Therefore, he could prove the theorem if the order of if the P is a divisor of the order of the group, then there is an element of order P, etc., etc. So Lagrange was doing the following. He started with the rational function, then and took in some permutation, and then applied. Let me write sigma phi. Sigma phi is by definition phi of, you permute the variables. This is new rational function. Now, if this was different from phi, keep it. If it is equal, just throw it. Then take another permutation and do the same thing. So, and he wanted to go on like this, and question is how long he can go on, or what is the least number he has to stop. So, in our language now, it's very easy. That means he has taken phi and he has taken the orbit of phi. Orbit of phi under this action. So, in our notation, remember it is Sn multiples of phi. And his question was, what is the cardinality? That was what Lagrange wanted. And he could guess clearly that this is a divisor of n factorial. But he could not prove this, and that is what led in general to the orbit stabilizer theorem. Now it is very clear that this is a divisor of, because this cardinality of this orbit is same thing as index of the stabilizer in this group. So this is again the notation is Sn suffix phi. This is the stabilizer of phi, that is the cardinality of the orbit, and this is clearly a divisor of the order of, this divides order of Sn, which is, we know it is n factorial. So this was Lagrange. It started by Lagrange. Lagrange did not prove this precisely, and his student Abbot, he proved it finally. And later on in the standard textbook on finite group theory, you will find now the Lagrange's theorem, which says that subgroup, order of a subgroup of a finite group divide the order of that group. This is what it came into the existence. Okay. So now what do we want to do? We know that Sn operates on this field, rational function field. So we write like this. This 2k x1 to xn, there is this operation map. And whenever group are operating on the set, the most important to find the fixed element. So what is, now I have a field, this is the field k x1 to xn, this is an extension of k, this is a very big field and this group is operating there. So I want to find what are the fix Sn k x1 to xn, and this is contained here, that is obvious, the constants are going to be constant, and this. And now there are so many questions. So for example, we can ask about this field extension, namely, is it finite? If it is finite, what is its degree? Is it Galois? What is this Galois group? And so on. All these questions are cropping up. So the first question I want to understand, I want to concentrate, is what is the fixed field. So I want to describe this fixed field, the description of this fixed field. That is what I want to do. And not only Lagrange, there were many people involved in this. And the main people involved in this, right from the Newton, Vitte, or van der Monde, Gauss, etc. All these people were involved in this to understand this. And the theorem which I will write, that theorem is in those days it was never written up precisely, but it was sort of known that everybody knows it. The first written proof you can find only in a Gauss's writing. So that is the. So for that I want to give some examples of fixed points of these fixed elements in the rational function field. So that at least to start with. So those are precisely called elementary symmetric polynomials. What are they? So note that this action of Sn on the rational function field, it is also, if I restrict to the polynomials, it also goes to polynomials. So Sn also operates not only on the rational function field, it operates on the polynomial ring also. So the first one, S1, look at the sum of these variables. It is obvious that if I permute the variables, this S1 will not change. So therefore it is clear that this one belongs to the fixed points of Sn and the polynomial ring. And another thing I want to note here, even this field is not playing any role. You could take arbitrary ring and this group is operating on this polynomial ring over arbitrary ring K, and this polynomial is the sum of the variables. It is clearly fixed because when I permute the variables, this polynomial is not going to change. Now S2 is, now you take product 2 at a time. So that means this sum xi, xj, and this is running over all the indices I less than j. So product 2 at a time, and I could have chosen so this is clearly fixed, because if you interchange the variable, this product will go to some other product which is also part there, and so on. Similarly, I can go on till Sn. This is the product of all x1 to xn. If I had to write R in between SR is what? R at a time. So, that one should write it as summation running over the tuples I1 to IR. So, this is running over I1 less than IR. I can always order them according to the increasing order and write in that fashion. So, all these polynomials, they are fixed under the action of Sn, and they are called elementary symmetric polynomials. Now, the theorem says, so this is the theorem. This, if you see the writing of Newton, you already feel that he knew this, and this is Newton, and it must be in around 1965-66, not 1665-66. What does it say? That the fixed field of the operation of Sn on the rational function field in n variables, this is nothing but the field generated over K by these elementary symmetric polynomials. This is what the theorem is. I will soon prove it. So, this is also known as fundamental theorem on symmetric polynomials. This is very important theorem, and later on I will use this theorem to prove that the field of complex numbers is algebraically closed. Let me also say that this inclusion is clear, because all these are, we know that all these S1 to Sn are fixed under the operation of Sn. So, therefore, if I take any polynomial in S1 to Sn, they are also fixed under the operation of Sn, and therefore, all rational functions are also fixed. So, I also should write that Kx, the ring generated, the algebra generated by S1 to Sn over K, this is a polynomial. This is also the fixed Sn polynomials, K x1 to xn. And therefore, why this theorem is so fundamental? Because it explains all the polynomials which are symmetric. Now, when do you say a polynomial is symmetric? You say a polynomial is symmetric if it is invariant under all permutations of the variables. So, let us recall f, a polynomial f over k in many variables is called symmetric if f sigma of f equal to f for every sigma in Sn. And what is sigma of f? Where sigma of f is by definition, look at that f and permute the variables according to that sigma. So, f is not changing under every f, under every sigma. That means this condition means orbit of f is singleton. So, we should also write it, and I am going to write in a modern notation only. So f is symmetric if and only if orbit of f equal to singleton f. And this theorem therefore explains, so examples of symmetric polynomials, are all these polynomials S1 to Sn are symmetric, and they are called elementary because they have got the definitions of S1 to Sn have got by very elementary way that S1 is the sum, S2 is you take product 2 at a time and their sum, S3 is product 3 at a time and their sum, and so on. So they are called elementary symmetric polynomials. And the theorem says if you know this, then you know all the symmetric polynomials. They are precisely the polynomials in this S1 to Sn. So, but you take any polynomial g, and instead of you take any polynomial in n variable g, and you take g of S1 to Sn. This is symmetric, and precisely these are symmetric. That is why that theorem is very fundamental, and it will have lots of consequences. And one will also imagine that if you want to study polynomials in n variables, this group operation is very, very important. And why was it so important to consider this polynomial also? That also I will explain before I prove the theorem. Okay, so before I prove, why is this so important to consider for the study of the zeros of a given polynomial? So, given any n natural number, a general polynomial of degree n is the polynomial Fn. This is by definition, this is the general of degree n. So, what do we write? It is a monic polynomial. So, x is a variable, it is only in one variable, minus x1, x minus xn. So, this is, think of this as a polynomial over, this is a polynomial in x with coefficients in where? With coefficients in the polynomial ring in the remaining variables. But this one is contained in rational function field and the polynomial over that in x. So, this is a polynomial of degree n, it is obvious, and the coefficients I am considering this rational function field. And now, when I expand it, what do I get? When I expand it, even when I multiply it out this product, what do I get? X power n, it is monic of degree n. The next coefficient is what? That is minus S1, x power n minus 1. The last coefficient is alternating, last coefficient is minus 1 power n Sn. So, let me write it on the next page. So, this polynomial is Fn is x power n minus S1x plus alternating Rth term will be minus 1 power R Sr, this is n minus 1, this is n minus R, and so on. The last term will be minus 1 power n Sn. This is general polynomial. So, if I want, to study this polynomial Fn, I have to study the symmetric functions, elementary symmetric functions, because now what? If I want to find, if we know the zero of this polynomial, then what will be the coefficients? So therefore, if somehow I know x1 to xr are zeros of a polynomial f, of monic polynomial, that is like this. Zeros of f is one variable polynomial over some field, I should write L, some field L. This is a one variable polynomial, and suppose I know the zeros, they may be in a bigger field. These zeros may not be in a L, but they may be in a bigger field, say E. Then I know this, but when I expand it, what do I get? I will get x power n, and the next one will be minus s, but this s1 evaluated at x1 to xn. That makes sense because this is a sum, and so on. Last term is minus 1 power n, capital Sn evaluated at x1 to xn. So, this gives you a relation between zeros on one side, on the other side elementary symmetric polynomials. Right? This correspondence. If I know the zeros, I know the elementary symmetric functions evaluated there, and if I know those coefficients, our problem is to relate them to the zeros. This relation was already known to Vitte. So, simple case let me show you, and that is what we want to generalize now. So, suppose I have a quadratic x square plus bx plus c. So, x minus x1 times x minus x2. We have written this in a bigger field. This was in a field kx, let us say. Then we have enlarged our field L to k to L, and then we have written this there. And what is the relation between b and this? So, obviously, this b equal to minus x1 plus x2. This is S1 evaluated at x1, x2. C is product of 2 with a sign. So, minus 1 power 2 x1, x2, which is S2 evaluated at x1, x2. And then, if you remember, we were considering the discriminant of this. So, discriminant was what? Discriminant was b squared minus 4c. This was the discriminant. And our school formulas depended on the square root of this discriminant. So, that means what we want to study the discriminant also. Now, this discriminant is what we can write in terms of this S1, S2 and so on. So, we need to go on this arbitrary degree polynomial, and therefore, we want to study elementary symmetric functions, we want to study symmetric polynomials. The discriminant may not be symmetric. So, I want to do this more general setup, and to do that, what is very, very important is to consider the group action of permutation group on n letters, on the polynomial ring in n variables, and also rational functions. And this is what I started with. We have to prove that theorem on symmetric functions, Newton's theorem that we have to prove. I will draw a lot of consequences from that, and I will also define a discriminant of a polynomial. More generally, I will define, given two polynomials, how do we find they have a common zero or not. To do that, I will also define resultant of two polynomials and the relation with zeros and so on. So, this is what will go on for couple of lectures from now. So, I will stop here and we will continue this in the next setup. Thank you.